how contributors get paid to the 000 project. Yeah. Users of 000 shouldn't really think hard about routing. They should just pay for the system and then expect high quality service. But of course, 000 still needs to be able to provide efficient and direct routes between users, and critically, it needs to be able to incentivize network contributors to provide the right connectivity. So how does it do that? How does 000 abstract away connectivity for the end user, but still provide the right incentives at the network contributor level? Let's dive in. To illustrate, let's begin with a simple example. Let's say that there are 3 cities, cities A, B, and C. Let's say that each city needs to communicate 1 gigabit of traffic to its clockwise neighbor. And then let's also say that they're already connected by the public internet, and the public internet takes 30 milliseconds to communicate. Now let's say the 000 network comes along, and there's a bunch of extra network contributors atop it that provide connectivity. First, a network contributor offers to connect between A and B, and does so very efficiently with a 10 millisecond latency. Then let's say there's a blue contributor that offers to connect B and C. They provide slightly better latency than the public internet at 20 milliseconds. Third, let's say a red contributor offers to connect A and C, and they provide latency of 25 milliseconds, only slightly better than the public internet. And finally, there's a brown contributor that also offers to connect A and B, again with not great latency, let's say again 25 milliseconds, or only slightly better than the public internet. How should these different network contributors get paid for their contributions? The first one might look like a checklist of sorts. It might be a very prescriptive model. It might say if you have a connectivity of 10 milliseconds, we'll pay you this. If you touch city A, we'll add on an extra bonus. If you touch city C, we'll add on another bonus, and so on. This, as you can tell, is an incredibly non-scalable way to do so. Every city, every permutation, every topology will require a lot of manual and centralized intervention to figure out what the right payment should be to different network contributors in the system, and that just won't work. A second model you might have in mind is the carried traffic model. If there's 1 gigabit of traffic transversing this network, and it always runs on the fastest paths, the purple path, the blue path, and the red path, you might think that those 3 providers should simply split the rewards 1/3, 1/3, 1/3. But that doesn't also seem very fair or efficient. The brown link, for instance, does provide some insurance value to the network. It may not be the most performant, and it may already exist on a corridor where there's better connectivity, but if the purple link were to go away for some reason, brown would be very important. Moreover, it doesn't seem fair that we compensate all of these providers equally when one has a very performant link and one only marginally beats the public internet. So this system too doesn't work for 000. 000 does neither of these. It instead opts for a third approach, and that third approach has 2 core ingredients. The first is a value function, and the second is a baseline. Let's start with the value function. The value function we don't need to look too hard for, it's just IBRL. It is literally the summation of traffic times negative latency. It is a combination of bandwidth and latency, nothing more. And then what's the baseline? Well, that's also simple. That's just the public internet. That's the status quo. That's what would happen if 000 did not exist. And with these 2 ingredients, we can now compute 2 manifestations of the value function. The first is where only the public internet exists, and that gives us some baseline of what value would be created if all traffic has to go over the public internet. And the second is where the 000 network exists. And we measure improvements from the public internet baseline to 000, and those are the improvements that network contributors have brought to the table, and so they are eligible to receive rewards on the basis of. The final component is to take these improvements from the value function and allocate them out fairly to different network contributors. This is where we use a concept from cooperative game theory called Shapley values. Shapley values are actually the gold standard for allocating value fairly. And in fact, they won their creator, Lloyd Shapley, a Nobel Prize in economics some years ago. At essence, what they look for is the marginal improvement from every given contributor. If a contributor didn't exist, how much worse would the network be? And it does so under different permutations and different topologies of creators. You can learn more about this at this GitHub link, 00 foundation/network Shapley if interested. And so now when we go back to our original example, we have a much better system. We can now reward contributors who do provide redundant links, even if those redundant links aren't being used to actively carry traffic. We can now reward contributors who beat the public internet a lot by a lot of rewards. And those who beat the public internet by just a little also just get a few rewards. And those who don't beat the public internet at all, well, they don't do anything to this value function, and so they get no rewards. And we can do all of this by maintaining a very simple approach rather than a complex list of parameters and particular carve-outs and ad hoc adjustments. All of this is possible with this simple network Shapley algorithm. And so this is the heart of how the double zero network stays efficient and dynamic. Network contributors are always incentivized to provide connectivity along busy corridors that beat the public internet and that are unique compared to its peers. There is no notion of incumbency, there's only dynamism in this network, and that's what allows the double zero system to evolve, just like the distributed systems that run atop it.